Hello, my name is Robert Smith, and I'm presenting our paper, Improved Bounded Model Checking of Timed Automata, on behalf of myself, as well as co-authors Marcello Bersani, Matteo Rossi, and Pierluigi Sampietro. So, timed automata are a useful model used for representing real-time systems. This can be any physical or computer system that needs to receive events and respond to them in real time. So what are timed automata themselves, though? Timed automata are essentially finite state machines that we have expanded with real valued clocks as well as bounded integer variables. So we can see a simple example on the right. We have two timed automata in a network together. On the left, we see one that has two states, Q1 and Q2, and we see a transition T1 from Q1 to Q2 that assigns a value of 0 to clock X. So when this transition is taken, clock X is reset back to 0. In the bottom state Q2, we see what's called a state invariant. And this invariant enforces the condition that while state Q2 is active, clock X must be less than 2. So state Q2 can only be active for 2 units of time. And depending on the model, that could be seconds, minutes, etc., before we must transition out of state Q2 and into another state. We see also transition T2 has a clock guard stating that this transition can only be taken when the value of clock X is greater than 1. We also have assignment to an integer variable. We increment the value of n by 1, as well as a synchronization action with another timed automata. This is a quick overview of the features that are supported in timed automata today. Now, once we've written a model of our system using timed automata, we usually want to verify some properties about this system, how it's going to evolve throughout time. Maybe we want to express a safety property to ensure that certain properties are always true. So what we'll be talking about in this paper is using MITL, Metric Interval Temporal Logic, to represent these properties that we'd like to verify. And we have a brief example again here at the bottom, where we have a property that states globally from 0 to infinity, so at all positions in time, the following statement is true, that if Q2 is active, if that is the active state, it implies that in the future, sometime in the next 2 units of time in the future, state Q1 will be active. And this is simply encoding that state invariant, that X must be less than 2 in state Q2. So within 2 units of time, we must transfer to another state, transition out of state Q2. So TACK is a bounded model checker. What's a bounded model checker? Well, these timed automata can have infinite traces. They can evolve forever in time. So we want to represent that with a bounded finite model so that we can prove that we can solve for these properties to determine whether or not they are true. So the way we do this is we take the infinite continuous time and break it up into discrete moments, the discrete moments when transitions are taken. So at the exact instant transition is taken, we record this, and then we record the gap, the amount of time between that and the next transition, or the next instant of time that we model. So now we've gone from an infinite number line to an infinite number of points. And to make this a finite model, we insert a bound. So we say that we are only interested in infinite traces that eventually loop back in on themselves. And what this allows us to do is represent an infinite amount of time with a finite number of points. So that gives us the bounded model checker. TACK aims to be an UPL-compatible solver. UPL is the current state-of-the-art tool for timed automata verification. And what makes TACK different is that it uses CLTLOC, which is a Linear Temporal Logic language, as an intermediary step. So both the TA network and the MITL property are encoded into CLTLOC. Some optimizations are done, and then this intermediate language is then compiled down to an SMT input language for use by an SMT solver. SMT is an extension of the traditional SAT solver, or Boolean satisfiability solver. And what those do is they, given a prepositional expression, for example, A and not B and C, they try to find a mapping of values to those variables such that the statement is true. SMT solvers is a simple extension of this to include real valued variables, as well as bit vectors, real arithmetic, integer arithmetic, etc. So The two inputs are converted into the intermediary CLTLOC and then translated again into an input language for the SMT solver. And there's a standardized SMT input language called SMT-lib that is supported by a wide variety of free available SMT solvers. So the problem with that system is that CLTLOC has shown to be a bit of an inefficient intermediary system, or intermediate representation, especially for the networks of timed automata. And so in this paper, what we've done is we've directly encoded the TA network into the SMT input language, into the BitVector logic that we use to represent how the timed automata transition and change over time. This allows us to remove the unnecessary CLTLOC semantics from the system, and then at the end, we can simply directly concatenate these two outputs. So the TA network is directly converted into the BitVector logic. The MITL model, the MITL property, is converted first into the CLTLOC intermediate, then that is then converted into the BitVector SMT input. These can simply be concatenated together and then given to the SMT solver. In addition, since we're directly encoding our TA network into the SMT language, we are able to do some more effective optimizations. First is we make a more extensive use of BitVector logic to reduce the state space that we have to search. So the way we've implemented this is that for any given property we want to express about our TA network, our timed automata, we represent as a bit vector, where each position in the bit vector represents the truth value of that statement at a certain point in time. So as we see on the right here, we can have an example property foo, and for a bit vector of length 4, this might represent a run of TACK with a bound of 4. We record the truth value of foo at every instant of the system. And so this lets us record and verify properties, for example, that we always take valid transitions. We only take transitions when their guards are true, right? When we take a transition, we ensure that we actually respect its variable and clock assignments. These are how all these formulas are represented to the SMT solver. And this carries a big advantage over the old way that TACK did this, which was representing these as real numbers. By using bit vectors, the SMT solver can convert those into propositional formulas and more effectively optimize them. And essentially what we're doing is reducing the state space it has to search to make it more efficient to solve these properties. In addition, we were able to remove some unnecessary state that we had. So previously we had represented both the active transition as well as the active state for each timed automaton in the network. However, each transition already encodes its source and destination state, the source and destination of the transition. So given that we already know which transition is active, we don't need to separately track which state is active. We can just look at the source of that transition. This allows us to, again, shrink the state space further and further optimize our solver. In addition, we were able to make some improvements over the original TACK implementation. The original TACK solver did not actually support full arithmetic for integer variables. Integer variables previously could only be tested for equality, but they could not be tested for less than or greater than relationships. So we fixed that in the new TACK iteration. And we've also cleaned up some of the synchronization logic to enable one-to-many synchronization, whereas before there was a flaw in the one-to-many synchronization logic. So next, I'll present some of the more interesting constraints that we had to model as part of the TA network and show how we encoded those semantics and what decisions were made. So the first one has to do with transitions. And an interesting question for when you're encoding this kind of system is, at the instant of transition, what state should be considered active? Well, if you don't have state invariance, that might not be as important. But when you do have state invariance, it becomes an interesting question. We see at the bottom here we have two states in the network. The first one has an invariant saying that the clock x must be less than 2 when that state is active. The second one says that the clock x must be greater than or equal to 2. So clearly there's only one point in time when we can safely make this transition, and that's at the exact instant where clock x is equal to 2. But now at this moment of transition, the question of which state is active suddenly becomes very important. So what we've decided is that in TACK, every timed automaton is in exactly one location at every moment is in exactly one state, one location at every moment of time. This includes at the moment of transition. So essentially you have a choice. At the moment of transition, you can be in either the source or destination state. And if you need that, for example, in this example model, that's very important. We need to be in the destination state at the moment of transition to ensure that these state invariants are respected. So TACK allows you this extra flexibility, if you need it, to model more complex properties. If you don't need this, we offer the possibility to, at the beginning of the execution, set every timed automata to always be, for example, in the destination state. So we can take that choice away for you if you want. That will reduce the state space that the solver has to search, but it will, of course, also disable these kind of more interesting situations and properties you can model with this feature enabled. Another important feature for networks are synchronization between different actors. This is critical in many real-time and real-world applications. So as I mentioned before, we support two types of synchronization, one-to-one, as well as broadcast or one-to-many synchronization. We'll give a quick overview here of one-to-one synchronization and how it's implemented. So any time automata, any transition can synchronize over a channel. Here the channel is represented as alpha. And for one-to-one synchronization, we have two actions. A sending action, which is an exclamation point, and a receiving action, which is a question mark here. So what the top expression is saying here is that for all transitions in our network, if they synchronize with a one-to-one sending action, then the following statement is true. If the TA is active at a certain point of time, no other active transition can be sending over this one-to-one synchronization channel. So there's only one send per channel at a time. In addition, there must be at least one active transition that is receiving this one-to-one synchronization over a given channel. So that ensures that the sender and receiver are both transitioning simultaneously, which is what we want. On the bottom half, we have the same thing, but from the point of view of the receiver. So if a receiver is active, then no other active transition is receiving. And in addition, there is at least one sender. We also at the bottom have another requirement, which is that both the sender and receiver have the same type of edge. And that's what we just talked about before, whether they're in the source or destination state of the transition at the time of synchronization. So that's another requirement of synchronization, another way that that edge implementation, the source or destination choice that we've implemented, can feature into more complex properties, more complex system dynamics. So moving on to the results. So in our paper, we compared our algorithm against the original TACK solver as well as the earlier MITL BMC. MITL BMC was the first solver that supported MITL properties, which we've inherited a lot from. In the original TACK paper, when TACK was originally introduced, it was compared against MITL BMC and found in general to be faster. So although in our paper we do compare against both, for simplicity in this presentation, we'll only show the comparison between ourselves and the original TACK. So the newer TACK algorithm, the older TACK algorithm. The benchmarks we used represent real-world applications. So the Fischer Protocol is a mutual exclusion protocol when multiple actors are attempting to gain exclusive access of a shared resource. The carrier sense multiple access with collision detection. This is an algorithm that's part of the Ethernet standard, and it is modeling multiple agents trying to communicate over a shared bus. In addition, we have the token ring model. This is a fairly simple model where we have a group of agents arranged in a ring. They pass a token between themselves that represents exclusive access to, again, some sort of shared resource. And finally, we also have a gearbox model. This is a model of a realistic automatic transition machine, a car, that has a gear interface, so you can set the gear to reverse, neutral, first, second, etc. Those signals get sent to a gearbox controller. This gearbox controller then has to coordinate the actions of the engine, the clutch, as well as the gearbox itself to ensure that these gear transitions are handled safely, and if errors are detected, to fail in a safe way. When possible, we tested these with varying model size and time bound. So the time bound, again, is the number of states we can search before we have to find a loop. The varying model size for protocols like the Fischer Mutual Exclusion Protocol as well as the token ring, we can vary the number of agents in either the ring or competing for the shared resource. So we can model that as well, and that gives us another dimension to test how these different algorithms, how these different solvers scale with larger inputs. So the SMT solver we used for these tests is Microsoft's Z3 solver, which is a freely available industry standard or industry strength SMT solver. We found that this is a very CPU bound process. So we have very little memory usage. On average, we have 20 to 200 megabytes, which is not very significant for a modern machine. And this is a single core process. So you do not need a fancy 64 core machine to run these tests. They can be done with over-the-shelf commodity hardware. So the first set of results we'll look at is the Fischer Protocol. And here, again, so for Fischer we have both a varying bound, so the length of the traces we can search for, as well as the number of agents in the Fischer Protocol. So here we presented the results varying with respect to the bound. So as the bound increases, we see for most of the properties we see an increased speedup. And here these values are the geometric mean of the runs with different numbers of agents. So we have 5 liveness properties, and these liveness properties essentially are guaranteeing that the shared resource is never deadlocked, and that there will always be another process gaining the resource at some point in time. The safety property, on the other hand, is trying to ensure that no two processes can gain access to the shared resource simultaneously. So it has to be an exclusive access to the shared resource. So we see, in general, as the bound increases, we see a better speed up from the newer TACK algorithm, suggesting that it's better equipped to handle larger networks as well as larger bounds. The one exception we see here is the safety property, where we do substantially worse in the beginning. Towards the end, these asterisks represent when tests were not able to be completed within our 2-hour time limit. So we do not have values for these as they took too long to execute. So some theories for why the safety property is different. This is a more complex property to encode into MITL, and it's possible that with larger bounds, more time, we may see some improvements with the newer algorithm as well. And here we see the same results, but varying the number of timed automata. So here, again, we see a similar story where with very few timed automata, with a very small network size, we see essentially equivalent performance between the older and newer solvers. However, with larger network sizes, with more agents in the network, more timed automata in the network, we see improved performance from the newer algorithm. The next model we'll look at is the Gearbox model. So the interesting differences between the Gearbox and Fischer Protocol. The Fischer Protocol is making heavy use of the bounded integer variables in its model. And this is something that, as I mentioned before, we were able to optimize with our BitVector representation. The Gearbox model, on the other hand, does not make use of these bounded integer variables, and instead it's mainly focused on having a large number of states, a large number of agents, and complicated synchronizations between these different agents, the different components of the Gearbox. So here we see a similar but a bit more complex picture. We see for certain properties, we see improved performance as the bound increases. We also, for example, property 4, we see initially the newer algorithm gets worse, and then there's a point where it begins to get better. And we see that at bound 40 or 50, we see speed of 2 or 3 with the newer algorithm. However, for other properties, we're either unable to determine, or we see a slightly worse trend for the bounds that we were able to compute within the 2-hour time limit that we see. So the third we'll look at is the CSMA Protocol. That's Carrier Sense Multiple Access, the protocol that is in the Ethernet standard. Here, unfortunately, the older TACK algorithm cannot compute this property because of the defects found in the synchronization and bounded integer variable comparisons that we mentioned earlier. So instead, we decided to test the different options that we've enabled for end users in the newer TACK algorithm. So as mentioned before, end users have the choice to enable or disable that choice of which state is active at the instant of transition. So we also allow people to choose if they want to further reduce the liveness constraints on the TA traces considered. So if you want to restrict the model to only look at situations where every timed automaton makes at least one transition within the loop, that's possible, and that will restrict the state space, allowing you to do a faster verification but of course you will not be considering certain cases. So here we've compared CSMA with the most restrictive set of options we have against the most inclusive set of options we have. And we can see in general, the more restrictive options allow us to compute the property on average in about half the time, so a speed up of 2. And in some cases we see a speed up of 5, in other cases we see about the same. So this is just going to show the amount of features we've added for end users to customize TACK to meet their requirements, to meet their verification standards, and the amount of time they have to compute these properties. Some conclusions: we've implemented new encoding for the networks of timed automata. We're directly translating these timed automata networks into the final SMT format. In general, we've seen a faster performance as well as better scaling to larger networks, as well as higher bounds. We've especially seen better performance with the use of these bounded integer variables. For models that you make heavy use of these, we see a much larger speed up. And in addition, we've been able to enable more options for end users to be able to customize and control the computation time as well as the state space of their system. Some future work we'd hope to do. For the internals of the system, it would be nice to similarly re-encode the MITL property. Because again, right now we are directly encoding the TA network into the SMT format. However, the MITL property is still done through the intermediate step of the CLTLOC language. So it would be nice in the future to translate both of these two components directly into the SMT language to further simplify the system. In addition, we'd like to have support for superint semantics. This is something supported by UPL that essentially allows a timed automata to make multiple transitions in a single instant. So a TA could go from state A to state B to state C, all in the blink of an eye, at the same point in time. Whereas in our system, after every transition, there must be a time delay. And with this is the last piece, the last missing piece to get full UPL compatibility, so that every UPL model will be able to be run in TACK. So this is important for us. The third feature we'd like to enable is what's called incremental verification. This is something that's done by MITL BMC, and we can see that essentially with incremental verification, we first look for counterexamples. If we have a bound of 20, we'd first look at a bound of 1, and if we can't find anything at bound of 1, we look at a bound of 2, and then a bound of 3, and then a bound of 4. Now normally this would be incredibly inefficient because at a bound of 4 you can still find counterexamples at a bound of 1. But essentially what MITL BMC has done is it's encoded this property in a way that when it's looking for things at a bound of 4 or at a bound of 5, it excludes all the solutions that can be found at smaller bounds. So it checks incrementally increasing the bound and only checking the solutions that weren't possible at previous bounds. So this allows you to find short counterexamples quickly. For example, currently TACK, if you have a bound of 20, but a counterexample can be found at a bound of 5, TACK first has to expand that counterexample to a length of 20 before it can be verified and returned. So we see for short counterexamples, we see MITL BMC having a faster performance than TACK because it can return early, whereas TACK has to solve the complete trace up to the full bound. In addition, we'd like to enable further ease of use features for end users. So currently, we do not verify the bounds for the integer variables. And if your model goes over the bounds that you tell TACK, TACK will have undefined behavior. And essentially what happens is that eventually these bounds will wrap around, because we're using 2's complement representation, into the negatives, or if you go too low, into the positives, and the semantics of your system will be incorrect. So we'd like to have a tool to fix mistakes that you may make and automatically detect when your system could go over your bounds. In addition, we'd like to have support for TA templates in your input file, and this just makes it simpler to model something like a mutual exclusion protocol when you have multiple agents that are essentially doing the same thing. It just allows you to write that template once and then instantiate it multiple times. So that's just an ease of use feature for the programmers making these timed automata models. With that, thank you very much. I look forward to answering any questions you have.
Okay, so welcome to the live Q&A for this talk. So thanks, Robert, for, well, not so much for the presentation because it was a video, but for getting up at 6 a.m. in California to assist this question and answering.
Of course.
which is really very much appreciated, of course. Well, some questions before you can have breakfast. So in the chat, there's a question by Marie-Christine. I don't know if she is here to ask the question herself. It doesn't seem to be the case. So I will just read the question. So the question is as follows. The speed up does not seem to increase monotonically, but sometimes seems to drop for larger bounds or larger number of timed automata. Can you comment on this?
Yeah, so on the screen here, you see the slide for the speed up versus the number of timed automata, and you see it does seem to drop a little bit from 8 to 10. And the reason I think this is that the original algorithm is very variable in its results. So for a lot of the tests, it actually took slightly longer for 8 timed automata than it does for 10. In comparison, if you plot the results on a chart, the newer algorithm is a bit more consistent in that regard. So I believe the 8 to 10 difference is just an artifact of that variability. And after the paper, we did run it to a bit higher bounds, and we're pretty confident that's the case.
That seems like a satisfactory answer to me. If not, then we will see some activity in the chat. So I also have a question for you. So I read in the paper, in the conclusions about future work, which, as I learned, will most likely not be done by you then, but so you wrote there, or you and your co-authors wrote there, that you would like to investigate some kind of incremental approach to model checking. And I would like to know if you have any more, if this was based on any insights that you had on how to do this exactly, because as far as I know, combining a bounded model checking, incremental model checking is not completely obvious. So do you have any insights on that?
Right, it's a pretty difficult issue because you end up, there's so much overlap, right? If you try to solve it for a bound of 10 and then you want to increase that to 11, the problem is that you're checking a lot of the same scenarios again.
Yeah.
And there's a couple ways you can mitigate that issue with our standards, with the setup we have now, where you can, for example, one way to like make smaller solutions longer is to simply unroll the loop. So you enter the loop a state earlier, and the state before you enter the loop ends up being the last state in the loop. So it's a duplicated copy, so you can add extra states. And you could add a constraint preventing that. There's still a couple other ways that make it, a couple other workarounds like that make it more inefficient. The way the MITL BMC tool does this at the moment is they use the SMT solver YACES, which has built-in support for adding and removing constraints after you've already begun solving. So you could start with a large bound, right, and then constrain it to only look at the initial 10 states, and then relax the constraint, so it looks at 11 and then 12. So it's still a bit inefficient, but I believe that's probably the best approach.
So do I understand well that it means that actually you refine, let's say, your task, your analysis task incrementally? Is that what you're saying?
That's how we would do it. At the moment, when we run the tool for a bound of 25 and then for a bound of 30, we start everything over. So for a bound of 25, we have exactly 25 positions. How that other tool does it, that does have incremental solving, is that you give the max bound 30, it allocates space for 30 states, but then it starts by only allowing the solver to use 10 of them, then 15, and so on.
Okay, I see. Yes. That makes sense. Okay, I personally don't have any other question. I see any other questions in the chat right now. So, well, I can ask for one more question, but so I know some of the benchmarks that you dealt with, but not all of them. So, do you think the size and the way the characteristics of the benchmark had a strong influence on the results, or I think I read something about that. But
yeah, the original TACK paper was only run with 3 benchmarks, one of which was Fischer, which you see here, and the other 2 were the CSMA and this token ring simulator.
Yeah.
And in the paper, we mentioned that the CSMA benchmark actually ended up being incorrect. So one of the things we wanted to
we lost you, I think. Okay, so thanks